Okay, now please don't look ahead if you haven't already seen this, but there's a question up here. If depth changes from 10 centimeters to 6 centimeters in 5 seconds, then at what average rate would we say the depth is changing? Well, let's just take that. You should pause and think through this question. But here's the answer we're going to go on now. The depth changes by how much? -4 centimeters. From 10 to 6 is -4, and that negative is important. Most students in class said, well, it changes by 4 centimeters. Yeah, that's the magnitude of the change, and that's a perfectly good answer. But when we're analyzing functions and doing rate calculations, it's important to know whether the rate is positive or negative, so we know whether the quantity is increasing or decreasing. And if it is increasing, the rate will have a positive sign to indicate that. If it's decreasing, the rate will have a negative sign to indicate that. So, depth changes by -4 centimeters in 5 seconds. Now, what would you say is the rate at which it changes? And in what units would you measure the rate? Well, the rate is simply going to divide the -4 centimeter change by the 5 seconds. So you get a rate of -0.8, because -4 over 5 is -0.8, and centimeters over seconds is centimeters over seconds, which can be read as centimeters per second. Per indicates a division of this quantity by this quantity. Okay? So that makes a certain amount of sense as the rate at which the depth changes. If the water is going down quickly, you're going to have more centimeters in fewer seconds. That's going to give you a bigger rate. Now it's going to have a greater magnitude. It might be a negative, but it's going to be a negative of greater magnitude when the water is going down faster. And then as the water slows, you're going to have fewer centimeters and maybe in more seconds. Or fewer centimeters in the same time, lots of ways, but it's going to tend to get smaller. Okay? Now, next thing I draw is I draw a picture of this situation. Now, when I originally drew the picture, I didn't have the yellow line there, so let me go ahead and just get rid of it. And here's the start of the original picture. Now, what this picture indicates is what? Now, there's an arrow here from the axis up to this point, and an arrow here from the axis up to this point. Well, the picture indicates this situation. If the depth is the quantity that's plotted in this direction, then the 10 centimeter arrow represents the initial depth, the 6 centimeter arrow the final depth, and the 5 seconds here represents the time interval, the 5 seconds during which the depth changes from here to here. Now, the depth probably doesn't change at a uniform rate. If this is a flow situation, you know the rate is slowing. But we're going to say, okay, over this 5 seconds, there is some change in the rate, but not a lot, and we're going to go ahead and just approximate this by a straight line from this point to this point. So what we have is essentially a graph of that kind of shows the rate of change by this yellow line, or this yellow line segment, and the time duration and so forth. It gives us this information, the same information we had when we posed the original question. So now I ask, what's the slope of this line? Don't read the rest of this stuff. Think yourself, how are you going to get the slope of that line? Well, the question I then ask is, what's the first words that come to your mind if I say slope? And people say rise, run. Okay, slope, as you know, is rise divided by run. So to answer the question, what's the slope, you're going to have to break it down and answer the question, what's the rise and what's the run? Well, what is the rise from this point to this point, and what's the run? Well, you should see pretty clearly if the rise goes Well, you're at 10 centimeters, then you're at 6 centimeters. The rise is the change in the vertical direction. The change is downward 4 centimeters. So the rise is negative 4 centimeters. What's the run? Well, the run is how far you go in this direction to get from this point to this point. And as we see, that's got to be 5 seconds. So the rise is negative 4 centimeters, the run is 5 seconds, so the slope is negative 4 centimeters divided by 5 seconds, which is negative 0.8 centimeters per second. Now, this is something that we've seen before. What's this mean? This is the average rate at which the depth changes with respect to time. Okay? So this is our average rate. Okay? And there's more words that go with that, and I'll write them offline and come right back. Okay, what I've just written is the slope is the average rate of change of depth with respect to clock time. Okay? We see that the slope is downward. We see that it's negative 0.8 centimeters per second, and that represents the rate of change of the depth with respect to clock time. Now, I didn't say the with respect to clock time before, but that's kind of an important thing because we have different situations where we have one quantity changing with respect to another. And that's not even a terminology that you're very accustomed to at this point, but it's important to understand what those two quantities are because that tells you what the rate of change means. Okay, now what's the shape of the figure I have here? Well, just to make sure we really understand it, I've drawn the figure again in purple. And I have the 10 centimeters, the 6 centimeters, and the 5 seconds here. And I also have the negative 0.8 centimeters per second in a little box up here. Okay? So these are labeling conventions. What do you call this figure? Okay, well, people, I think, pretty much knew that was a trapezoid. In this case, I'm going to call that a graph trapezoid. Okay? It's a graph trapezoid. It's a trapezoid that's part of a graph. Now, to put that in context, if you have depth versus clock time, and you have a graph where you have your depths versus your clock time, we can go point to point on this graph and connect the points, forming a series of trapezoids. And this series of trapezoids gives us some really good information about the graph and about how the graph and the rates of change and other things are related. Okay? Now, this isn't an accurate graph because, as you know, the actual depth versus clock time, or at least as you strongly suspect, actual depth versus clock time is a smooth curve that only goes through these points here, 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 and here. And I didn't draw that real well. The curve is a little bit below the points the way I drew it. But you understand that if you have a curve like this that goes through all 4 of these points, that it's going to be a little bit below the straight lines because of the curvature. Okay? Well, the point is then that we can break a graph into trapezoids, and by understanding what happens in each trapezoid, or in a typical trapezoid, we can understand a lot of things about what the graph is telling us that we wouldn't otherwise understand. So, I'm calling this a graph trapezoid, the kind of trapezoid you would get if you break a graph up like so. And it has a quote graph altitudes. Okay? And those altitudes, what do you think the graph altitudes would be? Well, altitude generally goes up. That's why I call this a graph altitude. But then I have another graph altitude over here. There's a graph altitude to the left, on the left side of the trapezoid, and on the right side. So the graph altitudes correspond in this case to the depths. And I'll tell you why I've got the quotes around the word graph altitude in a minute. But then we also have the width, which is 5 seconds, and the slope, which is labeled by putting it up here near where the slope is and putting a box around it so we know it means slope and not something else. Okay, and that's just a convention I use. It's not a convention anybody else in the world is likely to understand, but it's a handy way to think about this and to label the relevant quantities here. Okay, now, I'm going to digress a minute. Why did I put quotes around graph altitudes? They look like altitudes. Well, this thing is a trapezoid. Now, where are the altitudes of a trapezoid? How do you know you have an altitude of a trapezoid? What's the definition of an altitude of a trapezoid? Well, it isn't this, and it isn't this. These are not altitudes of this trapezoid. I call them graph altitudes, okay? The altitudes of a trapezoid, and nobody seemed to know this, and I commented a little bit on how if you've had a geometry course and don't understand what an altitude is and can't tell me what an altitude is, you need to think about geometry with a little more focus. Not your fault. It wasn't taught that way. It was taught with a bunch of vague ideas rather than good, focused, rigorous definitions. Okay, and geometry, one of the values of a geometry course is you do get a bit of mathematical rigor, and when you don't get that, I think you're missing something. Anyhow, and I don't blame your schools, I don't blame your teachers. It's a national thing. I blame everybody in the nation for listening to people who don't know anything and try to dictate the curriculum. And their politics, parents want all the children should be above average. Some of the responsibility goes on them. I'm not going to stay in that soapbox here, but that's the idea. Okay, now the definition of an altitude of a trapezoid is the distance between the parallel sides. Now, you measure the distance between two parallel lines perpendicular to those lines. So we could also say the perpendicular distance between the two parallel sides, although the word perpendicular would be redundant there because the distance between two parallel lines has to be measured perpendicular to those lines. In general, an altitude is measured perpendicular to a base. Okay? Now in this case, we say the trapezoid has two bases, and you measure the altitude perpendicular to the bases. And the altitude would therefore be the 5 seconds, and the 10 centimeters and 6 centimeters would be the altitudes. Okay, so if you're trying to use the formula 1/2 B1 plus B2 times whatever the width is, W or whatever, depending on who writes the formula, it's not going to agree with the idea of altitudes here. Okay, that'd actually be 1/2 base 1 plus base 2, which is the average of these two, multiplied by the altitude, which is not the width. I said width a minute ago because I wasn't thinking. Okay, well, just understand that these graph altitudes are not altitudes of the trapezoid. They're altitudes on the graph. You don't really have to know it, but the width of the trapezoid is, in fact, its altitude. Don't let that be too confusing because the idea is pretty straightforward, and we'll go on with it a little bit tomorrow anyway. Okay. Now briefly, we go back to this picture. I put 3 boxes here. If we do the altitudes, or the y values here, the graph altitudes, this one, this one, this one, and this one, then we would know the graph altitudes for each trapezoid. If we knew the coordinates down here, if we had the x-axis labeled or the horizontal axis labeled, then we could figure out the run for each trapezoid. If we had these altitudes, graph altitudes labeled, we'd easily be able to find the rise. So we'd be able to find the slope, and we could fill the slope in, the 3 slopes in with these 3 boxes, and perhaps see a trend in the slopes.